So this is combination of section 3.7 and 5.7 since in this course textbook, this is where we're really highlighting inverse functions. And so our learning objectives here, we have five, which I subtly spoke about earlier, but now we'll get to go into more detail with this. Being able to verify inverse functions and determine the domains and ranges of them, which is the same as just finding the domains and ranges of any function. It's just you're now dealing with a special type of function. Being able to evaluate inverse functions from the technical standpoint, from a tabular standpoint, from a graphical standpoint, and then using the graph of one-to-one functions to graph inverse functions. And then last but not least, restricting domains, because a lot of functions in the world do not pass the horizontal line test, aka they're not one-to-one. However, if we do restrict the domain along a certain interval for the graph, then it does pass the horizontal line test and we can find the inverse of that particular part in the function itself. So we have some definitions here, and I think I'll read this slide. So our inverse function, formal definition, is for any one-to-one function, y is equal to f of x, a function f inverse x. This is not f to the negative 1. This is just the notation for inverse of f of x, is an inverse function if f, or there's a typo here. It should be inverse function of f if f inverse y is equal to x. So sounds a little confusing. All you have to think about is if it passes the horizontal line test, you can find the inverse, and the inverse switches your x's and y's. And we'll do some fun examples in a moment highlighting that. So then we have to have an inverse function f of x, it must be one-to-one. It's a very, very crucial requirement. So it has to pass that horizontal line test. And then we have some fun facts dealing with domain and range. So if f has a domain A and a range B, then when we're looking at its inverse, it's the opposite. The inverse has a domain B and a range A. Anytime you're dealing with inverses, think about reverse engineering. You're undoing what the original function has done in the first place. And then the last sort of note is the fact that f to the negative 1 does not mean 1 over. It's just, again, notation of representing an inverse function. Okay, so let's start off with our example 1, where we're given a one-to-one function and we have f of 2 is equal to 4. And then we also have f of 5 is equal to 12. We're asked to find the corresponding input and output values for the inverse function. Again, inverse function, once we're given it's one-to-one, we have an inverse. So switch your x and y values, and then boom, you have your answer. which means f of 4 is equal to 2. And I should look at it from inverse notation. So f inverse 4 is equal to 2. And then f inverse 12 is equal to 5. Question? Yeah. Right. Now we have our inverse function properties. And so let's use pink. Let f be, once again, one-to-one function. I know I didn't write it yet, but I'll write it over here. Passes horizontal line test, so you guys don't forget. With domain A and range B, the inverse function f inverse satisfies the following cancellation properties. So think of composition of functions now. F inverse of f of x is x, where x is in the domain of f. And then you can do the reverse. F of f inverse x is equal to x, where x is in the domain of f inverse. So any function f inverse satisfying these equations is just simply the inverse of f. And so down here it goes into a little bit more detail, but if you're able to compose f of g of x or g of f of x, and one of them is true, then both of them are true, and we have that f and g are inverses of one another. And that's a really, really cool property. If you're able to compose it and one of them works, then we know that the two functions are inverses. And we'll practice that in the example on the next page. If one is false, then it automatically doesn't work. Okay. So we want to show that f of x and g of x are inverses of one another. So the key takeaway is just find the inverse of one of the functions. And if it ends up equaling the other, then amazing, it works. So we're going to find the, find the inverse of one of these functions. We'll do f of x. So f inverse of x. How do we find the inverse? These are the step-by-step procedures. So finding inverse. First step, switch your x and y variables. And just keep in mind, y is just the same as your f of x or g of x or h of x. So y equals f of x. And then your second step is you want to isolate your new y. And then your third step is you want to put into proper inverse notation. So first step, we want to switch your X's and Y's. So I'm gonna just start, maybe bring this guy all the way down because that's our last step. F of X is the same as Y, so we have Y plus 1 over X plus 2. And when we switch it, we now have X is equal to 1 over Y plus 2. Now we want to isolate our new Y. So we want to get Y by itself. X as a fraction is X over 1. So what we can do is let's cross multiply. So we're looking at X in parentheses Y plus 2 is equal to 1. Opposite of multiplication is dividing. Divide both sides by X. So now we're looking at Y plus 2 equals 1 over X. And we want Y all alone. So our last step is we're going to subtract 2 from both sides. So we end up getting Y is equal to 1 over X minus 2. And so our last step is to put this into proper inverse notation, which is F inverse of X is equal to the 1 over X minus 2. Now, is this the same as our G of X? One over X minus 2? 1 over X minus 2? Yeah, it is. Therefore, F and G are inverses of each other. And we're done. Any questions on this? Second objective, finding the domain and range of inverse functions. If you're able to find the domain and range of the original function, then the domain and range of the inverse is just the opposite. What the domain of the original function is, it's the range of the inverse. What the range of the original function is, that's the domain of the inverse. So we have the range of a function is the domain of the inverse function. And then vice versa, the domain of the original is the range of the inverse. So now let's do example 3 together, where we're asked to find the domain and the range of these inverse functions. So we're given the original function, which is 2x plus 3 over x minus 1. And we're given the inverse, which is x plus 3 over x minus 2. We want to find the domain and range of both functions. I'm going to just put f of x, domain. And this question is to just really solidify your understanding that they end up being opposites. And then we have our inverse. So remember, when you're finding domain, you want to think about your restrictions. Can't be undefined, so no zero in the denominator. And if there are any square roots or radicals, can't be negative underneath that root sign. We don't have to worry about the roots here since there are no radicals, but we do have denominators. So with our f of x, we have that x minus 1 cannot be equal to 0, which means x can't be equal to 1. That's our only restriction for our domain. Which means, what is our domain of f of x? Negative infinity up to 1, but not including 1, union 1 all the way up to infinity. And we're done. What about for our inverse function? Well, now we can't have x minus 2 be equal to 0. Which means x can't be equal to 2. I wrote only domain. I should have wrote only restriction. This is our only restriction. X cannot be equal to 2. So how do we put this into interval notation? We have negative infinity up to 2, not including 2, union 2 to positive infinity. Now to find the range, we could graph out these functions and then look at all of our possible y values. But based off of this definition, it's quite straightforward now. We know that these two are inverses of each other. The question gives us that. So what's the range of f of x then? Yeah. And then what's the range of our inverse function? Got it. So as long as you're able to find the domains, the inverses, when dealing with inverse functions, the ranges are right there behind and no work is required. It's just flipping. Any questions on this one? No. So once again, if we know we have a one-to-one function, then we can find its inverse. And then we can pull bunches of data from that. However, if we don't have a one-to-one function, we can do something called restricting domains in order to find inverses. And that's what we do a lot in this course and just dealing with functions in general, because most functions don't pass the horizontal line test everywhere. And so before we go into that whole restriction of domains, let's look at inverse functions from a table standpoint. So we're given this f of t function, which shows distance in miles that a car has traveled in t amount of minutes. And we want to find and interpret f inverse of 70. So if we're dealing with the inverse function, just remember your x and y values are flipped. So instead of looking for 70 under t minutes, we want to look for 70 under our miles. So it's really that last column that we're honing in on. And so our F inverse 70 gives us what? Gives us 90. And so let's interpret this. What does this tell us? That when we travel 70 miles, how long is it going to take us? Yeah, exactly. 70 miles is traveled within a 90-minute time span. This is a graphical representation of finding inverse. So we're given our g of x graphed below, and we're asked to find g of 3. So when our x is 3, our g is at 1. But then we're also asked to find, okay, well then what's g inverse at 3? And so again, instead of viewing this as your x, you now want to figure out, okay, when our y is 3, what is our x? That gives us 5. So again, x and y values are switched when dealing with inverse. Put this down here under solution. And then this is kind of what I wrote out before when we had to find the inverse of that previous function. But this is the step-by-step procedure in finding inverses of one-to-one functions. And then we have a note here saying, sometimes you'll need to know an inverse function for all elements of the domain, not just a few. If the original function y equals f of x, that's our just general formula, then we can often find the inverse by solving to get x as a function of y. How do we do that? We have y is equal to whatever combination we're given. We switch or we swap our x and y. We now isolate our new y, and then finally we put it into our function notation and we get our inverse. So let's practice that example again, except now we're dealing with a much more straightforward function. No fractions. Are given f of x is equal to 3x minus 2. This is the same as y is equal to 3x minus 2. Now we want to swap. So we're looking at x is equal to 3y minus 2. We want to isolate our y. So let's add 2 to both sides. So we're looking at 3y equals x plus 2. And then let's divide both sides by 3. So now we have y is equal to x plus 2 over 3. And then our last step is to put this into proper inverse function notation. Our inverse of f of x is simply x plus 2 all divided by 3. And we're done. do another example. So f of x is the same as y. We have y is equal to x plus 1 over x plus 5. Next step is swap out your x and y's. And then now we want to isolate our y. So x as a fraction is just x over 1, so that we can go ahead and cross multiply. Tribute. Bring all the y's over to one side. So I'm going to go ahead and subtract 5x and then subtract y. So we're looking at xy minus y is equal to 1 minus 5x. And then that left-hand side, they both share a y, so I'm going to factor out a y. And then the opposite of multiplying is dividing, so I'm going to divide both sides by x minus 1. That I finally have y all by itself. We have 1 minus 5x all over x minus 1. And then our very last step is to put it back into proper inverse function notation. So we get f inverse of x is equal to 1 minus 5x all over x minus 1. And we're done. Yeah, the tricky part of this is you may not see it very clearly at this step. And so you sort of want to manipulate that left-hand side and then really factor out that y. Then you'll see it a bit more. Yes. Yeah, so right here I subtracted, the y over here. So I didn't do xy minus y, I just did xy minus y like that. Yeah, I just had, it looked like it was stacking as if that cancels out, but no, it's just, I wrote it out, yeah. Any other questions? We have example 8, where we're dealing with Fahrenheit and Celsius and inverting it. So that we can sort of see, okay, instead of plugging in Fahrenheit to get your Celsius, what if we just plugged in Celsius to get your Fahrenheit? It's a very useful formula to know, especially if you travel a lot. So how do we do this? Again, swap your C's and F's. So we're now looking at F is equal to 5/9 C minus 32. And then you want to isolate your C or isolate your new C. So here, I would actually, because 5/9 is a constant, I would divide both sides by 5/9. So that you're essentially looking at 9F over 5 is equal to C minus 32. And then you can go ahead and add 32 to both sides. So you get your new C to be 9/5 F plus 32. But you don't want to forget to put it into the proper inverse function notation. So it's going to be C inverse is 9/5 F plus 32. When you're done. About 8 more slides for this section. This section is quite long, actually. Finding inverse functions and their graphs, which is part of the fourth objective. And so we have the graph of F inverse is obtained by reflecting the graph of F along the line y equals x. So just to recap back before, dealing with even and odd functions, even reflects across the y-axis, odd functions reflect across both the y and x-axis, aka the origin. And then inverse functions reflect across the line y equals x. Y equals x is not the origin. It's completely separate. So, very important fact. And down here is just a visual representing that. We have our line y equals x, and if we have this weird f of x function, if you just reflect it across, this is the inverse of that weird f of x. So now let's try and put that into action. We're given f of x down below here, and we want to just sketch a graph of its inverse and then state the domain and range for both f and f inverse. So what I like to do is I like to sketch in my y equals x line of reflection. And I'll label it too, y equals x. And then from here, then it'll be a little easier for me to find the reflected part. So this 1, 1 over here, sort of like this 0, 1 over here. And then again, it's a sketch, so it doesn't have to be perfect. But I'm going to put in this point as well to make it a little easier for me. Okay, should be good. So it's going to look something along these lines. F inverse x. And this was our f of x. So now from the domain and range perspective, what do you think our domain of f of x is? All of our possible x values are, doesn't hit 0, but comes quite close. So it's 0 to infinity. And then what about our domain of f inverse? Negative infinity to, yep, pretty much now tells us what our range is. What's our range for f of x? It's just our domain of f inverse. And then what is our range of f inverse? It's just our domain of our f of x, right? And we're done. Okay. And then finally, we're on the last objective where we are finally restricting the domains of a function to make it one-to-one. And I know I've said it so many times, so maybe I'll have a student read this part for me in yellow. Thank you.
Function is now one. It has no inverse function. Sometimes, no inappropriate restriction on the domain of such a function yields a new function that is one-to-one. Then the function defined on the restricted domain has inverse functions.
Good. So yeah, we're going to be practicing restricted domains so that we can indeed find the inverse along that interval. So we're asked to find the inverse of this quadratic function x squared if our x is greater than or equal to 0. We're going to graph f and f inverse. And so graph of f we know quite well. And then we want to graph its inverse. Again, when you graph the inverse, this is 1, 1. We're reflecting it across that line. Y is equal to x. Seems about right. Sometimes I'm like the worst drawer in the world. And let's solve it technically as well. So same exact procedure. We have y is equal to x squared. Flip your x's and y's. X is equal to y squared. Isolate the y. And so you get y is equal to your plus or minus square root of x. Put it into proper inverse notation. So you get f inverse x is equal to plus or minus the square root of x. I could maybe draw it a little bit better. It's just hard with the line of reflection there. Any questions on this one? This is just a slide on the step-by-step procedure when you're restricting domains that are not one-to-one. So just like here, right, this fails the horizontal line test. And so we have to end up restricting the domain so that when we do find the inverse, we're still dealing with the function. And that's why I put in plus or minus square root of x, but really we should be neglecting that negative part so that we can still deal with a function. So if we restrict it by restriction, or I'm going to write by domain restriction, we're looking at the inverse function to be just the square root of x. And I'll put in the positive, but usually they don't put positive in. You're just expected to know that it's positive square root of x. Go back. Okay. So we have some more examples. Find the inverse function of f. We have a part A and a part B. Again, write it in terms of y, swap out the x's and the y's and solve. Now, in this particular example, you're going to have to use your knowledge of FOIL. Well, do you? No, I wouldn't. I would just go straight into taking the square root. Makes it much easier. And then last but not least, put it into that proper function notation. And they give you that x is greater than or equal to 4, so that that domain that we can actually find the inverse, that domain is restricted. F inverse x is equal to the square root of x plus 4. And then we have here that x has to be greater than or equal to what? In this example, though, right? We're looking at the inverse. This was before, this was dealing with now the range of the inverse. But now if we're looking at the domain here, what's our domain of our inverse? It can never be what underneath the square root? Yeah, so x has to be greater than or equal to? Yeah, exactly. Right, part B. Y is equal to x minus 4 squared. And now that's looking at the negative when x is less than or equal to 4. So we're just breaking up the two different functions. So we don't have to do the math for this all over again. Maybe we should highlight that this is positive. And this one in part B is going to be negative. So we end up getting y is equal to negative square root of x plus 4, and then our inverse. Our negative square root of x plus 4, where x is greater than or equal to 0. Again, from a visual standpoint, I'll show you guys in a moment, and then I'll come back to this slide. But that's just comparing the square root of positive x versus, positive square root of x versus negative square root of x. This is our positive square root of x versus negative square root of x. Again, no negatives should be underneath that square root, which is why we have that x is greater than or equal to 0 in both cases. Say that again?
How did you find it?
Good question. Anytime you take the square root of both sides, what's the square root of 25? 5 or negative 5. So
But how do you know, like, for this problem, is it just because the x can't come for equal?
well, because you have those two solutions from a graphical standpoint. You have the negative and positive. In algebra, we really hone in on the positive value because we're dealing with money or distance. And so we always, I would say like 90% of the time, we're always neglecting the negative. But when it comes to a graphical standpoint, we're at this stage in math where you really can't neglect the negative anymore. You want to offer the two solutions. The one that's more common is the positive square root of x. But it's important to know that you really have positive or negative when you take the square root of both sides, because you're dealing with quadratic. Quadratic functions have two solutions all the time. And so we're just always, I guess over the years, we always honed in on that positive solution, but now we're at a level where, okay, we can accept that there's two different cases. Right, inverse of a radical function. So notice that the functions from previous examples were all polynomials and their inverses were radical functions. If we want to find the inverse of a radical function, we need to restrict the domain of the answer because the range of the original function is limited. That's just a fancy way of saying it fails the horizontal line test. And so that's why the domain needs to be restricted. And that's also the reason why we broke up this same function into two separate ones, because if we look at it from this standpoint, we get a function, versus when we look at it from this standpoint where x is less than or equal to 4, then we get this standpoint. However, if we look at them both together, then our horizontal line test fails, or actually not horizontal, our vertical line test fails, and then we don't have a function. And that's just again to represent over here, right? Our vertical line test fails here and here. But separately, if we just looked at this, works. Or if we just looked at this, then it works as well. And then down here is just the step-by-step procedure with finding inverses of radical functions. Again, it's the same as what we've been doing for linear functions as well. Okay, so we want to restrict the domain of the function. F of x is equal to x, the square root of x minus 4, and then we want to find the inverse. So how do we restrict the domain? This is where, once again, our toolkit functions are important. Because if we look at just the square root of x, we're looking at positive square root of x. And so the square root of x minus 4, that's a horizontal shift, left or right? It's to the right, right? And so we're really looking at this positive aspect, which means what's our domain? Our domain has to be greater than or equal to, well, with our toolkit, it's greater than or equal to 0. But with our x minus 4, it's going to be greater than or equal to 4, exactly. So this is our domain restriction. And then now we can just solve our inverse like we're used to. Put it in terms of y equals, and then swap your x's and y's. And then you want to isolate your y. And last but not least, you want to put it into proper function notation. So you end up with f inverse x is simply x squared plus 4, and then we're done. And so that completes this section 3.7 and 5.7. And so our next session or section is going to be 4.1, which is just dealing with linear functions.